think you can see this one, right?
Yes, I'm. Yes.
Okay. Guys, so last time we finished chapter 1 and that was the statistical modeling, scientific inspection and the graphical designs. So all these parts we have covered in chapter 1. And I just would like to request you on page number 31 of your book. Please try to go through some of the examples as a homework for chapter 1. That is example 1.17, 1.18, 1.20, 1.21, and 1.24. Just 5 examples. Page number 31 and 32 of the book. I repeat, example 1.17, 18, 20, 21, and 24. Go through these examples. They are really very simple, and that's why I don't want to go through this one. But I'm 100% sure that you guys can do this thing.
Okay.
Today we are going to start the new chapter, that is the probability. So first of all, let me let you know that what we are going to see here. The first of all, we are going to see the sample space, then the events, then I would say the probability and set theory, how the probability is defined based on the set theory, because that is very important, in which we are going to see the union of a set, intersection of a set, complement of a set. So all these things we are going to see the set theory from algebra in terms of this statistics, in particular probability. So in the study of statistics, we are concerned basically with the presentation and the interpretation of change of outcomes that occur in a plant study or the scientific investigation. We know this thing. We learned about this thing in the last chapter too. We shall refer to any kind, data like categorical data and non-categorical data. Non-categorial means numerical data. So we went over 2 data, numerical data in which the numbers are involved, continuous and discrete. Discrete means 1, 2, 3, 4. Continuous means whole real line without missing a single number, including rational and irrationals. And the categorical data in which the category is defined, but not the numbers, like eye color, mountains in the world, number of mountains in the world, then particularity of some city, name of the rivers. So these are the categorical. This is the category, which type of river is there, or this is the category. Skin color, this is the category. Statisticians use the word experiment to describe any process that generates a set of data. A simple example of a statistical experiment is the tossing of a coin. If you toss a coin, that means there are 2 outcomes, 2 possible outcomes. One is either head or tail. Am I right? If you toss a coin, so either head or tail, there are only 2 possible outcomes. These 2 possible outcomes are known as the sample space. They are the elements of the sample space. I told you last time, in the first chapter, that samples are always or sample set is the subset of the population. Here we are talking about sample space, means collection of all the sample elements just in terms of one set, that is called this, or in the space, that is called the sample space. So that's what we are talking about. So whenever we have this type of experiment in which we toss a coin, once we toss a coin, 2 outcomes are there, possible outcomes. One is head, one is tail. So H, that stands for head, T stands for tail. So H and T. These are the only 2 outcomes. I'm going to write these things on the whiteboard. Just wait. Then after we can think about another example. So another experiment might be the launching of a missile and observing of its velocity at specific times. So launching the missile and observe the velocity at specific time at some different interval of times, you can come to know the different velocities. So there is also a categorical, of course, based on categorical, but you can also define the sample space based on this one. So number of things are there. So this study, I would like to start with the definition of a sample space. So let me start with the definition of sample space, and whenever things require at that time, we will switch over to the book or my slides. So first of all, let me first go through the slides, and then after I would like to switch over to the whiteboard. So let me give you a brief idea about the chapter, the probability and statistics for engineering you know, chapter 2 probability. And if you do this thing, so first of all, we are going to see events, sample space, how to use the diagrams to count the sample points, complement union and intersections of the events or sets, you can say, but here in terms of statistics, we would say events, sets and their properties, multiplication, additive rules, permutations and combinations, very important thing, permutation combinations, very, very, very important, and probability of events, partition of sample space that is highly useful, conditional probability, that is for conditional probability and the independent events too. And finally, we are going to see the Bayes rule or Bayes rule, what you want to say. Then after, first part is the sample space. So this is the definition of the sample space. We are going to see all these things. The set of all possible outcomes of the statistical experiment. That is nothing but the sample space. So we are collecting all the outcomes in terms of a set. That is the sample space, and that is represented by capital S. Then after some tree, this is called tree diagram. We are going to go through this flipping of coin example and its tree diagram. Then after, we are going to see some practical examples. And then after, we will be switching over to the next one, that is the events. And event is a subset of a sample space. So look at over here. I told you in the last chapter that samples are nothing but the subset of population, and event is a subset of a sample space, right? So event is a subset of a sample space is a subset of a population space, you can say. Okay, and then after, you can see complement, some different types of set theory. We are going to see here complements, intersection, union, all these things. We will be switching over to this slide so also whenever time comes. And two events are mutually exclusive, or you can say disjoint. If there is no common part, you can see one event and there is nothing common in both of these events. A has nothing to do with the B and B has nothing to do with A, but they are from the sample space. And then after, important properties of the sets, and we are going to learn the statistical analysis based on this set theory. And then after, the last example that is over here, and we will go over this example too in particular. And probably that is the work for today. And then after, next time, we will start section 2.3. That is the counting sample points. So today's work is based on article 2.1 and 2.2. So let me start with my whiteboard. Okay, guys. So let me continue. So as I told you that if you flip a coin, chapter 2, chapter 2 probability. Okay, so as I told you that if you flip a coin, flipping a coin, there are two outcomes. Two outcomes, they are given in the terms of set. As I told you, either you're going to get H or you're going to get tail, right? Based on this one, I would like to give the definition. I give two examples. Another example, there was a launching of missile and we are measuring the velocity at different time intervals. So definition of a sample space, a set of all possible outcomes, the set of all possible outcomes at a statistical experiment, or outcomes of a statistical experiment is called the sample space. And that is denoted by, as I told you, capital S. And that's the reason I denoted here the sample space by capital S. So flipping of a coin, as I told you, that is one of the examples. So first example, as I told you, just the repetition, flipping coin, S is equal to H and T. Second example, tossing a die. If you toss a die, how many outcomes are there for tossing a die? How many numbers are there on dice? On the die, we have 1, 2, 3, 4, 5, 6. If you toss a die, if you roll a die, you're going to get either 1 or 2 or 3 or 4 or 5 or 6. So these are the sample space, right? These are the sample space. Suppose I want to go for the same thing, tossing a die, but not in terms of the numerical data, but I would like to go for categorical data. So this is the numerical data, but I would like to go for categorical. In that case, either if you toss a die, either you're going to get even number or odd number. How many odd numbers are there? Odd numbers are 1, 3, and 5. 1, 3, and 5. And other numbers 2, 4, and 6, they are even numbers. So if you toss a die, either you're going to get even number or odd number. So you can create a sample space based on the categorical or numerical data. So it's not like this there every time. And you can see the first time also it's a categorical. There is no numerical. So it both ways. I would like to give you another example, and I would like to go for a tree of this example. So idea would be more clear. So for that, let me give you the example. An experiment consists of flipping a coin and then flipping it a second time if head occurs. That means if you flip a coin, and suppose you are getting head. If you are getting head, flip it again. That's what it says. But suppose you are getting tail. If tail occurs on the first flip, then die is tossed once. Second time, so first time, if you flip a coin, if you are getting tail instead of head, suppose you are getting tail, that means you need to roll a die. So toss a die or roll a die, right? That means we have two outcomes over here. I would like to go for tree diagram of this one so that you will have the idea of tree diagrams too. So let me go for tree diagrams. Tree diagram. As I told you that flipping a coin, flipping a coin first time, or you can say first flipping a coin, you have two outputs, either head or tail. If you are getting head, flip again, flipping again. If you are getting tail, roll a die. Roll a die or toss a die. Toss a die. That's the question. That's the things. And suppose in the first trial, I'm going to flip a coin and I'm getting head. If I'm getting head, as you know that, again, I need to flip a coin, means again, I have two outcomes, either it is head or tail, and I have to stop. So this, I would say, this is my first outcome, and this is my second outcome. But instead of head, suppose I'm getting tail, then the question says that I need to roll a die. If I need to roll a die, that means I have 1, 2, 3, 4, 5, and 6. That means I have either one, because I'm tossing a roll, I'm tossing a die. So 1, 2, 3, 4, 5, and 6, right? So how many sample points are there? Look at over here. Now I'm going to write my sample points. So let me write it down over here. Sample points. You can see over here H and H. So that is my sample space, H and H. Then H and T. Am I right? Look at here. Look at my pen. H and H, H and T. Then T 1, 2, 3, 4, 5, 6. I'm going to get T1, T2, T3, T4, T5, and T6. And if I write everything that is in terms of a set with comma in between like this, that is space S, that is called the sample points. So tree diagram, that is the easiest way if you are working with some finite numbers and one or two or three events max. In that case, tree diagram, that is much more helpful to fix the sample points or sample space. Right, guys? So that is the sample space.
Yes.
Now, another example I can give it to you, that is the defective and non-defective items. So let me save this part and save PNG. Okay, and may I clear all these things? May I clear the slide? Clear all drawing. Okay, so now let's go for, let's change the color just to feel you good. Okay, so my another example is, suppose that 3 items are selected at random from a manufacturing processes. So 3 items are selected at random, manufacturing process. Number of items are being produced in the manufacturing process, and we are going to pick 3 items. Now, if you pick one of the items, that means one thing is there, whether that item is defective or non-defective. There are 2 outcomes, am I right? Exactly same thing will happen for the second outcome, second item. It could be defective, it could be non-defective. Third one, same thing, defective and non-defective, right? So suppose that 3 items are selected at random from a manufacturing process. Each item is inspected and classified defective as D and non-defective as N to list the element of the sample space, providing the most information that is given in this form. So I would say something like this, defective and non-defective. So my first item, suppose this is defective and this is non-defective. This one is defective and this one is non-defective. That is my first item. So let me write here first item. First item. And then after, I can go for the second item. So second item is, then it could be defective, it could be non-defective. I have the third item, again the same scenario, it could be defective, it could be non-defective. So it is third item. Third item. Okay, for non-defective, again the same scenario is there. Then after, for the second part, I'm going to get second item, it could be defective, it could be non-defective. And from here, it could be defective, it could be non-defective. So defective and non-defective, same scenario is over here. Then the third item could be defective, it could be non-defective. That means my sample points are, look at over here, D, and D, like this. So you can go for D, then D, N, and then N, D, then D, N, D, then N, D, and then N, D, then N. So these are the sample points. These are the D, N. Sorry. These are the sample points. And if you write this one in terms of a set, I'm sorry. If you write this one in terms of a set, so that is called sample space S. So that's how you can write this one. But sometimes it is not possible to write all the elements or all the sample points in the sample space. And that's why we need to write the same thing in the abbreviated statement. So statement, that is called the statement or rule method. So statement or rule method. Statement or rule method. As I told you that sometimes it is not possible, such that suppose I ask you, count the number of cities in the world whose population is more than 1 million. Now there are plenty of cities, more than, I would say, 2,000 cities, approximately, I don't know, but it could be 2,000 cities whose population is more than 1 million on the globe, around the world. Now, you cannot write all those 2,000 cities over here just in your sample set, sample space, because it's very time consuming and it requires lots of space as well as time. So that's why that is not possible. But if you write the same thing in terms of a statement, or if you make a rule, something like this, suppose my sample space S is equal to collection of all X, such that now X belongs to set of natural number. Why? Because you cannot say that 1.5 cities population are more than 1 million. It could be either 1 or 2 or 3 like this, but not 1.5, not 1.7. So it has to be set of natural number. So X belongs to N, such that X is a city with a population over 1 million. X is the city with the population over 1 million. 1 million, and set complete. So if you write like this, that means it is to be understood that we are just counting all the cities whose population is over 1 million in the world, like this. Suppose I give you another example. This is just one example. Let me give you another example. That suppose I have one circle. I have one circle with center 0, 0 and radius. Suppose I would say 2, radius 2, like this. Right? And I would like to count all the points over here inside and within and on the circle. That means I'm counting the points on the boundary of this circle as well as I'm counting the points inside the circle. How many points are there? You cannot even count it. Infinitely many points are there inside the circle. So infinitely many points, I mean, infinite number of points. Is it possible to write it down in one sample space? No, it's not. And that's why we require the statement or a rule. So I would like to write this one, that is equal to set S is equal to collection of all X order per XY, because we are counting 1 point from X-axis. This is my X-axis. This is my Y-axis. 1 point from X-axis, another point from Y-axis. So this is the point. Suppose it is 2 and 2. Or 1 and 2, something like this. So that's how all these points are being counted. So collection of all points X and Y such that X square plus Y square is less than or equal to 4. So this is the equation of circle well known. X minus 0 square, Y minus 0 square means X square plus Y square, circle with center 0 and 0 and radius 2. 4 means 2 square. So we are counting all the points such that X square and Y square and less than or equal to 2. That means it starts from here and it goes inside. It goes inside. So it's counting all the points from the boundary of the circle with the inner side. So that's how you can find the sample space. That's how the sample space is being defined. My second definition, that is the event. So now let me go for the second definition, that is the event definition. Okay. So an event is a subset of our sample space, as I told you. An event is a subset of a sample space. Let me take the example from your book, example 2.4 from the book, illustrative example. Let S is equal to collection of all t such that t greater than or equal to 0, of course, t greater than or equal to 0. And but what is this t? What is this t? This t is nothing but the life in years of a certain element or electronic components. Life in years of certain electronic component. Right? Certain electronic component. I told you, let me just first, I told you that suppose this is my whole population, then samples or sample space is a subspace of population and event is a subspace of the sample space. So it is something like this. So T is equal to life in years of a certain elements, certain electronic components, right? Now life in years, that means it could not be negative. Once you have one suppose I go to the market and try to take one light bulb. That means I cannot say there is -1, because once I start the light, once I switch on, means that bulb may run for 5 minutes, 10 minutes, 13 minutes, at least 1 second, right? Or maybe 1 year, 2 years. So it could be any real number, but positive real number. And that's the reason I just put it down over here, t greater than or equal to 0. It could be 0 too, because once you switch on the lights and immediately bulb is gone, right? So without just in fraction of second, bulb is gone. That means you cannot run that bulb even for a minute. So that's why we can say it is greater than, it could be 0. Most likely, practically, it is more than 0. And life in years, t is a life in years. So 1 year, 2 years. See here, it could be 0 year or 1 year, 2 year, 1.5 years. It could be anything. Years of certain electronic component, one of the examples. Then suppose I have another example of a complement of a set, or I would say subset of a set. So another example I would like to give you, that is event A is equal to those t such that 0 is less than or equal to t is less than or equal to or strictly less than 5. Strictly less than 5. There is no equality. Strictly less than 5. 0 is less than or equal to t is less than 5. Right? 0 is less than. This is my event A. This S is a subspace. I mean to say yes, sample space. Life in years of a certain electronic component. Right? So this is my S. This is my S. And t less than or equal to 5 means those components whose life in year could be between 0 and strictly less than 5. 0 and less than 5. So this is my A. But this is actually given in terms of real number R, real line R. Life in year, so there is 0. And all this number, they are my R, or you can say S. Sample space S. But my event A says that it starts with 0 and ends up to 5. It could be 4.9999 years, but not exactly equal to 5 years. Before a day of 5 years, 5th year, that bulb is gone or electronic component is gone, right? In that case, it doesn't go for a complete 5 years, at least something less than 5 years. So that's why I have to put the open interval over here. And that is my event A. And you can see over here, this event A is a subspace or subset of S. So that's what we mean by the event and relationship between the event and the sample space. Let me again save this one, and then after I can clear this slide and we can go for the next one. We can go for the next one. Okay. Next is null set. Null set. Null set that is denoted by either like this, means no element in the set, or usually people denote by phi. This is called phi. That is the null set. As per example, people are looking for the example of a null set. Suppose let me change the sample space B, that is collection of all x such that x is an even factor of 7. X is an even factor of 7. Now, how many factors of 7s are there? 7 ones are 7. Am I right? So that is only 7 and 1. These are the only two factors of 7. But it says that x is an even factor of 7. X is an even factor of 7. Is it possible to get the even number out of these two? No, it's not possible. That means my set B, ultimately it says that that is equal to empty set. There is no element. So it is null set. Null set. So that's what we mean by the null set. Then after, I would like to give you another definition that is called the complement of the set, or complement of an event with respect to X. So let me write down the complement of an event A with respect to sample space S is the subset of all elements of S that are not in A. That are not in A. People denote this one by A dash. Some people, they denote the same thing as A complement too. In a Venn diagram, suppose you have sample space and this is your event A. So A complement, that is this part, which are not, this is A complement, which is outside A complement. I can give you plenty of examples. One of the examples, suppose event R, a red card is selected from an ordinary deck of 52 cards. Let me write down for you. A red card is selected from a deck of 52 cards. Ordinary cards, deck of 52 cards. And this is my event, I would say, suppose R. This is my event R. And S is the entire deck. S is the entire deck. So you can see over here, entire deck means all 52 cards. Out of these 52 cards, how many red cards are there in the deck? In the playing cards game, how many red cards are there? 13 diamond and 13 hearts, right? That means 26 cards are there. So you can see over here, 52, 26, here there are 26, here there are 52 cards. So naturally 26 is a subset of 52. 26 is a subset of 52. So you can see this is the example of the subset, not the complement. Not the complement. I'm coming to that point, just wait. This is the example of the subset. Example of a subset. Okay. Then complement of an event. I just gave you the definition. We will discuss this thing after some time, because before that I need to define little more, two more things. Sometimes the complement that is defined like this also, this is sample space S, and suppose this is A. So the elements which are not here in A, that is here in A complement, like this. So elements which are not in A, right? Elements which are not in A. Suppose I am teaching, I can give you the complement example. Suppose I am teaching, this is my college class, sample space, my college class, statistic class, right? Sample space and statistic class. Now, or sample space of my university students. For STEM major, this is my one set. Now, this STEM major, they are the part of university student, right? Because they are in the university, and that's why they are identified either as science major or engineering major or math major. They are the STEM major. So what are the complement of STEM major? Non-STEM. So non-STEM majors, they are the complement. So that's what we mean by A and a complement. So non-STEM means immediately it could be, we can figure it out that if I say the non-STEM, that means we are not counting, or we are avoiding all engineering majors, all science majors, and math majors. And we are counting business majors, economic majors, blah, blah, blah. So they are the non-STEM, right? So that's what we mean by the complement. Another definition is, suppose, or another example is, now I would like to switch over to a little bit different, that is union and intersection. Suppose I have one sample space with the sample points, book, cell phone, MP3, paper, then after stationery and laptop. Stationery and laptop. And suppose I have one set A which contains, suppose book, and I would say stationery, and I would say laptop. Let me take paper also. Paper. This is my set A. I have another set B, or set A is this one, right? So I would say that this is my S, and my set A contains this one. So book is there, then stationery is there, then laptop is there, and paper is there. So how many elements are left out? There is cell phone and MP3. Agree? So this cell phone and MP3, that is B, or you can say that is nothing but your A complement. That is your A complement. So they are the members of the sample space, but they are not in A. That's why they are called in A complement. So I hope this idea is clear to you now, that A and A complement.
Yes.
Equal to book, cell phone, MP3, paper, stationery, and laptop. And some of the items they are in set A, other items. There is nothing common in both of these sets. Nothing common in both of these sets. Okay. So other way around, I would say that A intersection, A complement is a null set. We are going to learn about this intersection. Intersection means and, or you can say intersection. We are going to learn this thing. Another is A union A complement. A union A complement, that is always set S. Because if you count this one, if you count this one, and if you add over here A and A complement, that is equal to your sample space S. This is union. That means it is called or it is defined as union of two sets. Union of two sets. Two sets, union of two sets. So that's what we mean by the A and A complement. So now I would, as I defined union and intersection, so let me start the definition of union as intersection, union as well as intersection, and then after we are going to see the mutually exclusive sets in terms of some current events and with examples. So again, let me set this one. I'm going to say, let me save this one, and then after I can go for the another slide. Okay. So my next definition is, intersection of two sets or two events. We don't say sets because everything there is in terms of events because they're real life problems. So the intersection of two events, A and B, that is denoted by A intersection B, is the event. Is the event containing all elements that are common to A and B. And that's why I said intersection means, well, let me write like this, A and B. So intersection means and, A and B. As for example, suppose E is a set such that person selected is engineering major. Person selected is an engineering major. And F is a set that person selected is an engineering major and person is a female. Person is a female, right? So E intersection F, that is the set such that all females with engineering majors, am I right? All females with majoring in engineer or with engineering major or engineering majors. So that is my, if you want to plot the graph, you can plot something like this. This is my sample space S, and this is suppose my E. E is, there are some boys in engineering, person selected in engineering. There are some girls, those who don't have engineering major, psychology major, economics major, business major, like this. But there are some girls, so this is my F, but there are some girls having engineering major. So that is E intersection F. So E intersection F, that is just this portion. Just this portion. Second definition, or the next definition. Let me say all vocals, suppose A, E, I, O, U. A, E, I, O, U. And C is equal to some other letter, suppose L, R, S, T. Right? So naturally, V intersection C is the empty set, or you can say like this, phi. V intersection C is the empty set. That means if I plot the graph like this, suppose this is my S, this is my V, and this is my C. So this is my V and this is C. Nothing is over here because here we have A, E, I, O, and U. And here you have L, R, S, and T. Nothing is common. So if you want to write V union C, so V union C, that means you can count set V and then set C, but make sure that this intersection portion that could be counted only once, not twice. So I can write A, E, I, O, U and L, R, S, and T. L, R, S, and T. So that is nothing but the union. So V and C have no elements common. V and C cannot occur simultaneously. You can see here, since V and C, what should I write, have no element common, V and C cannot occur simultaneously together. Simultaneously. And this type of event that is called mutually exclusive event. Mutually exclusive events. And that's why this one is not the proper picture. Of course, it is A union B for V intersects V union C, it is good, but it is more better to define these two sets separately, V and C, A, E, I, O, U, and L, R, S, T, like this, because nothing is common between these two sets. So V intersection C is naturally empty set. Union is this one, but they are mutually exclusive. Mutually exclusive means A intersection B is empty set. Here, V intersection C is equal to empty set. V intersection C is equal to empty set. The definition in the book that is given in this form, mutually exclusive, one more definition. Two events, A and B, are mutually exclusive. Two events, A and B, are mutually exclusive, or you can say disjoint, if A intersection B is equal to empty set. A intersection B equal to empty set. That is, A and B have no elements in common. That is, A and B have no elements in common. No elements in common. Right, guys? Let me save this slide, and then after we can go for the next one. And let me clear this one, and let's start the next one. So now let me define union. So definition of union, already I gave you the definition, but more precisely as book words, the union of two events A and B, the union of two events A and B denoted by A union B is the event containing all the elements that belong to A or B or both. And that's why I told you union means or. So it is in A, so it is in A means this one, or it is in B is this one. So A or B, that means once you count this A, that means you don't have to count the same portion for B. So A or B or both. So A, that is this part, B means this part, or both means this part, That means we are counting each and every element of A and B, common portion just once. And plenty of examples. Already I give you one example. Another example is, suppose I give you set A is equal to A, B, C, and set B is equal to, suppose, let me give you B, C, D, and E. So naturally, if you write like this is my A, this is my B. Common part, first of all, you need to pay attention over here. So this is B and this is C. And then after here, it is A, B, C, D, and E. So you can see over here, my A union B, that is equal to A, B, C, D, and E. And that's it. A, B, C, D, and E. Okay. Another example, suppose I can give this example number 1, example number 2. Suppose P is the set such that employee from an oil drilling company smokes cigarettes. EMPLOYE, employee from an oil drilling company smoke. Employee smokes, CIGERETT, cigarettes. And my second event Q is equal to employee selected drinks alcohol. Employee selected drinks alcohol. Employee selected drinks alcohol. So what is P union Q? P union Q is equal to employee from the oil drilling company smokes, right? Smokes or either smokes or drink both, right? So set of all employees, EMPLO, set of all employees who either smoke or drink alcohol, either smoke or drink alcohol. That is my P union Q. P union Q. Another example I can give you. Suppose I have one set M is equal to those X from the set of natural numbers such that 3 is less than X is less than 9, strictly less than. And another set I have, suppose N, that is equal to those Y from the set of natural number that 5 is less than Y is less than 12. 5 is less than Y is less than 12. So naturally, what are the elements over here? So elements over here, 3 is exclusive, 9 is exclusive. So we have set of natural number, that means we have 4, 5, 6, 7, and 8. What are the elements over here? Naturally, we have 5 is exclusive, 12 is exclusive, 12 is exclusive. So 6, 7, 8, 9, 10, and 11. These are the elements, 6, 7, 8, 9, 10, and 11. So naturally, if I go for M union N, so M union N is equal to, what are the common elements? So it is 4, 5, 6, 7, 8, 9, 10, and 11. That is my M union N. And M intersection N, that is equal to 6, 7, and 8. 6, 7, and 8. So this way you can write like this, 6, 7, and 8. If somebody says that I want the picture of this third one, that sounds good. You can write something like this. You can draw something like this. Here it is M, here it is N, here it is X. 6, 7, and 8, they are common. So here it is 4 and 5, 6, 7, 8, 9, 10, and 11. So that is nothing but the Venn diagram. This is called, whatever we have been doing, sorry, that is called Venn diagram. That is called Venn diagram. Now I would like to give you one example, and we are going to look at some of the events and try to find that events in terms of the set theory, I mean to say intersection, union, complement, like this. So let me just remove these slides and let's go for the last slide for today's class. Rest of the things we are going to do next time. So let me just save this one. Okay. And my last one is, last example, I would say that, let me give you one picture. This is my set A, set B, and set C. All common is 1. 1 is common to A, B, and C. 2 is common to A and B. 4 is common to A and C. 3 is common to B and C. Here it is 6. Here it is 7. Here it is 5. 6, 7, and 5. Okay, now, if you can answer me this thing, I would appreciate. The first one is region 1 and 2. How can you write this one in terms of set theory? Region 1 and 2. Region 1 and 2, 1 is over here, 2 is over here. So we are talking about this part. Am I right?
Yes.
We are talking about this part. What is this part?
Is union.
No, that is intersection.
Intersection, yes.
Intersection. So that is A intersection B. Agree? A intersection B. Then after, let me give you another region. Suppose region, I would say 1 and 3. What can you say about this? Region 1 and 3 means this region. Region 1 and 3. What can you say about this? This corresponds to C, this corresponds to B, common portion of B and C. So I would say B intersection C. Agree?
Yes.
Okay. Then after, just try it. Regions, I would say, what? 1, 2, 3, 4, 5, and 7. What should be the answer? Region 1, 2. Then 3, 4. So common to A and B. 1 is common to all 3. Then common to A and C and common to B and C. 1, 2, 3, 4. And then I gave you 5 and I gave you 7. So except 6, everything. What can you say about this? 1, 2, 3, 4, 5, 7. Yes, any clue? See here, I have not counted this portion, this part of B. Agree? Yes or no? I have, hello?
Yes.
I have not counted this part.
Yes.
Right? So what I counted? I counted full part of A, I counted full part of C, including intersection and other sets, other elements in the sets too. So I would say it is A union C. Agree?
Yes.
Union C, that is this one, 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 and this one. Only B is not counted. So A union C. Same way, another region, suppose I go for region, yes, please, 4 and 7. 4 and 7. Region 4 and 7. What can you say about this? 4 is over here. 4 is over here. And 7 is over here. 4 and 7.
Is a union of A and C.
Union of A and C. If union, then 7 and 5 should be there, but 7, 5, 2, they are not there. 7, 5, 2, 3 are not there. Union A and C, they are over here. That means it should not be over here.
Intersection. Okay.
It should be intersection, right? But again, wrong, because if you count intersection, in that case, it has to be 4 and 1 only. 4 and 1, that's the only intersection part for A and C. But I gave you 4 and 7. I gave you 4 and I gave you 7. Do you understand me?
Yes.
So this is my 4 and this is my 7. That means you can see I'm just working on my set A, but I'm not counting my set B. Are you getting me? I'm not counting my set B. I'm just working on set A, and from set A, I don't want to count this set B, means 2, 1, 3, 6, they are just excluded. Shall I say, because elements, they are not in B, they are over here. See, elements we have which are not in B means B complement. Agree? So everything here, that is B complement. Agree?
Yes.
B. So I would say that B complement intersection. Now B complement means this whole part has gone. This whole part, this part has gone. Just remove this from the picture. So what is left out? 7, 4, and this one. So it is B complement, and I want just 4 and 7 that is included in A. So B complement intersection A, because B complement is outside all these things, all these things, not this one, sorry, not this one. And this 4 and 7, they are the part of A. So if I take B complement intersection A, that makes sense. Agree?
Yes.
Then after I would say that region, suppose 1, that is the simplest one, right? A intersection B intersection C, common to all three. Then after I would like to say, suppose region 2, 6, and 7. What can you say about this now? 2, 6, and 7. Two, 6, and 7. What can you say about this? 2 is over here.
Yes.
2, 6, and
yes.
7. So I'm counting only this part, 2, 6, and 7. I'm not counting this one. So shall I remove this set A? Set C?
Yes.
And then after 2, 6, and 7, I'm counting all these numbers, right? All the numbers of A and B. That means one thing is sure, A union B is there. A union B is there. But I want to exclude these numbers. So I would say that C complement intersection A union B. C complement, this is my C. This is my C. My C. And C complement means outside. Means all these things. This is my C complement. All these things. C complement is this one, including this and this. Out of this one, I just would like to count this, and this. So C complement intersection, if I take the common part, A union B. Does it make sense?
Yes.
So that's what we mean by the set theory. And we did up to, I would say that, exercise number 2.1, 2.2, I mean say article 2.1, 2.2. Homework assignments. Homework is 2.1, 2.2, 2.4, 2.11, 2.13, and 2.14. I think that is more than enough. These 6 examples are there in homework. So they are just based on this set theory. So if it is possible, try to go over these examples from the book, page number 44, page number 42, 43, sorry. Homework, page 42 plus 43 of our book. So that will give you much better idea than this one. And next time we are going to start article 2.3, that is a counting sample points. Let me again save this one. So save this one. Okay, and let me cross this one. And then after, let me stop sharing my screen. And I just would like to share my slides. So now you will realize this thing, that what we have done. See, we started with this one, sample space, chapter 2. Then after we went over. See, look at over here, event, flipping a coin. Tree diagram, same example. Few examples for your homework. If somebody is interested solving this example 1, 2, 3, 4, very simple, and try to find the sample space. See, throw 2 dice, record the result, 2 dice. That means you are throwing 2 dice at a time. That means on one die, it could be 1, second could be suppose 1, could be second could be 2, 3, 4, 5, 6. Then first could be 2, second could be 1, 2, 3, 4, 5, 6. First one could be 3, second could be 1, 2, 3, 4, 5, 6. Third one could be 4, second could be 1, 2, 3, 4, 5, 6. First could be 5, second could be 1, 2, 3, 4, 5, 6. Third could be, first could be 6, second could be 1, 2, 3, 4, 5, 6. So if you write all these things in the order pair, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, then 2, 1, 2, 3, 2, 4, 2, 5, 2, 6, then 3, 1 like this. These are the sample space. Same way. So this way you can just try to figure it out by your own, some examples for your own study. And then after, Okay. Then events, complement of a set, intersection, union. I put the figure over here, which gives you probably more idea in this color picture. Then after you can see the same kind of examples I took it in our class. Here I just changed the number. 2 is less than x. I gave you 3 is less than x is less than 9, and 5 is less than y is less than 12. Here I just changed the number and I asked you to find m union and m intersection n. Almost same thing. So it could be really very easy for you to. And then after mutually exclusive events, means intersection is nothing, no common part. Then after intersection, union, all these things, important properties, that if your set and union itself, that is a set itself, intersection of any set with the empty set is empty set, right? A intersection B complement, that is called A complement. Union, this is called De Morgan's law. A union B complement is A complement, intersection B complement. If you take the complement and its complement, means you are going to talk about the same event. Suppose I have one circle, sample space, and inside that I have one event A. If I go for A complement, means I'm going outside A. If I'm going for a complement, again, I'm coming back to that event A. So that's why a complement is A. And empty set complement means full space. Empty space is nothing. Full is complement means full set, everything. So that's the important properties for the set theory. This is the example we took. I asked you a number of things from this example, right? Region 1, region 2, region 3. I took this example 2.19. And 2.3 we are going to see next time. Thank you so much, guys, and I will see you next time. Let me stop my recording and